And then the today's models, the today's solutions, what we use today as a state of the art, those transformers came. Have you had any, let's say, previous information about transformers? I mean, I suppose that all of you know those systems, okay? Still, I would emphasize some parts of them. I'm not going to explain how those solutions work or how those architectures were built, rather just highlighting the reason why they are important. Okay, first of all, the earlier state-of-the-art solutions like LSTMs and CNNs, they had some limitations. As they worked with sequences, they could take a sequence one by one, piece by piece, which takes time. As a sequence, it's a time series, so it takes time. And that's why the performance of these models are quite limited. So we wanted to do something to speed it up and to have more powerful solution for that. And that was the original aim of transformers. To do things parallel, to make things faster, to make things more powerful. That was the original aim. But in the meanwhile, it turned out that it's not the only advantage they have, these transformer architectures. For example, they have an interesting thing which called attention. We wrote here point-wise attention. I will bring it back in the next slides. But before that, I would already mention that this attention, that makes our today topic possible, this prompt engineering part. I mean that we do only prompting. This attention mechanism, let's say that's the key for the whole system works. And of course, this context awareness also comes into the picture, that it's much longer range than before any kind of solution before that could cover in a certain text. You know, in the sequence models, it's quite limited how long sequence you can take, which is also written in the context window, and somehow a consequence of that these models could be taught with very, very big corpus pieces, or actually with the half internet, as you will see later on. But what does it mean? What was the consequence of that? One consequence is that the size really, at least in this case, the size does matter. Both sides. One side, the size of the data we use to teach a model. In the previous slide, you could see here some references, so I will not mention all the time those references, just later on feel free to use. But here I would refer to one, which is this one, the second one, which is summarized approximately here. Of course, I cannot summarize in one sentence a big document, but the whole point of that document is somehow here, that they try to teach models, different size models, different complexity models, assuming different capability models, because somehow the size of the model and the complexity of the model, that would lead to the performance as well. So they try to teach those models with different size of data sets. And it turned out that this chinchilla model, which uses approximately 70 million parameters, so it's a middle-sized model today. Years ago it was a giant one. Today it's not anymore a giant, but okay. And that model, with 4 times more data, could beat that time GPT. That time it was GPT-3, with 2 times, even 2.5 times more parameters. So a much more complex model, a much bigger model, assuming that much capable model, with less data, does not work so well. So it seems that data is more important than the parameters. Or at least, having the right data and having the right size of the data, that matters. But it's not about how big, but being optimal. If you read that paper, you will find some hints what is the optimal size of data sets for a certain model. Not to be, let's say, overtrained and not to be undertrained. There are quite good figures in that paper. At the same point, feeding these networks with huge amount of data, really vast corpus. Some new behavior emerged there, and that is the zero-shot learning behavior, which we'll talk about later. But shortly, it seems that we shifted the paradigm from fine-tune a model, or teach a model, to somehow just prompt a model and getting the model output or shaping the model output without having any tuning on that. That came also from on one side, it came from the size of the data we fed into them. The other important thing was, we already mentioned attention. Have you heard about this attention mechanism? All of you or none of you? András for sure, Benedict for sure. Okay, just quickly reminding you or just repeating most probably what you already know, that attention means that as we work with the sentences and words, we can look back what are the relations between the words and having a kind of an attention for the most important ones. And if you can see here this sentence, the animal didn't cross the street because it was too tired. So the model can have the attention that the it now refers to the animal. You can see there that the dark green here shows that the attention is on the animal. In the other example, the animal didn't cross the street because it was too wide. Here we have also an attention, but not on the animal, but more on the street. Did you get that? Okay, so in very short, this is the mechanism which helps the model to have that relations much better, like previously you have seen on the word vec, where just simply we have the general embeddings of the words. It really depends on that context. In this context, it means this one. In that context, it means that one. So, what is the consequence of that? That this attention could handle the local context in the certain text. So all those models which use this attention model, those are very good at the handling of the local context. Even more, they can do a phenomenon or show a phenomenon which is called in-context learning, which means that they can behave differently within the context as they do behave normally. Like you can see here that here in this, I don't know, can you read that? Okay, then I just tell you what is on the picture. So here we have a text. We try to predict the next part of the text. What the model does? The models look back. And when looking back, it means that within this context, it's important because we are in the context. Within this context, the same thing was mentioned, pot here from the Potter. It's from Harry Potter, I think maybe the first sentence of Harry Potter. We look back there and we try to catch what's the next. And we simply assume that within the context, what was the next is the most probable next again. And we just copy it. That is how the single layer solution of this attention or the induction head mechanism works. But it can do even more. If the architecture is so, like 2 or more layers used for that way, these models can do more than a copy. They can do even a fuzzy match, saying that let's look back what was there before and what was coming after, but not only for the same words, but for the similar ones. Ish. It's not, in this case, it was theirs, and here is quite the same, but you can see here that some others have also some attention before that. So it makes it even better because it says that they can keep the context not only for exactly the same words, but for the similar ones as well. Anything to add about that?
I highly encourage you to read this paper. It comes, I think, from the research of Christopher Olah, who was kind of famous when he was working on LSTMs. Everyone knows Christopher Olah's LSTM representation because that's how everyone knows about LSTMs. not from the original paper, but this is coming from Stanford and Christopher Ola. So this kind of phenomenon that he analyzed the exact working of what the attention mechanisms learn in a large language model, and though not the only mechanism he identified, the most dominant mechanism was this copy and like match and copy mechanism, and he calls this induction head. So that's where the name comes from, and I mean he showed that in a single layer only a literal copy is possible, and without two or more layers, this fuzzy match and copy is possible. So I think that the main takeaway here is that most possibly, even he kind of studied during the training how much time does have to be passing in the training after the first induction heads appear. And there is an interesting phase shift in the learning of the models, and the models become like suddenly much more good at completing a sentence when these induction mechanisms appear in the model first time.
There is a quite good YouTube video, I think, about that as well. And in that video, if you have some time, I think a 1 hour video or something like that, if you have 1 hour to go through that, he explains quite well that what kind of attention heads are in a transformer, which kind of head does what, like searching for opposite, searching for different, searching for something. But when it comes to the induction heads, which heads doing this copying and even this fuzzy copying, then you can measure in the loss that it's much better in context learning. But it's a sudden change there when those appear. So it's a quite good explanation on that. To be honest, for me it was easier to listen to him than to read the paper. To be honest, I would propose to you as well to ever listen to that video. Okay, what else was that? Well, okay, transformers came, they know what they know. We tried to feed vast data sets into those models. Even we found where could be the optimal size. Okay, we know how the attention works. Even these attention heads appeared on the horizon, saying that it helps to have some different understanding within the context. But what else we did? As normally we do, we try to form everything to our lookup, saying that it should be human. Okay, it's a machine, but it should look like a human. So we started to give feedback, a human feedback, and we tried to shape the models according to our thoughts or needs or values. For example, in this feedback loop, when we started to help the model to score which kind of answer, what kind of answers are good or bad, or better or worse, we try to shape. Try to shape the behavior of the model, or, for example, enforce the long-term coherence. What does it mean? The chat part from the chat GPT means that we have a longer chat, not just one question, one answer, but a longer conversation. So it should be coherent through the time. The model should remember what happened in the beginning of the conversation.
Say, for example, it was explicitly marked in the reinforcement learning through human feedback datasets that it's not appropriate when you say, "Hi, I'm John," and then the conversation goes back like 10 steps, and the model completely forgets that you are John. That people just downloaded this thing, like how dumb it is, it should remember. Basically, it's kind of an additional signal of pay attention more to the context.
And pay attention
more.
It's literal pay attention.
Literally reinforcing the fact that local context is the thing that people care about.
Yes.
And that's kind of overemphasizing the already given contextual learning of saying, look, this is the thing that you should learn more.
And by a side effect, as Levente just told, it strengthened this whole process, this whole loop, strengthened this in-context capability. And the result was actually, and here I come back to already mentioned the phenomenon that those are zero or few shot learners. So we don't need to fine-tune them to anything, or that's maybe too harsh to say to anything, but we don't need to fine-tune them in order to be able to do enormous amount of different tasks. It's interesting, I didn't know that before. Levente corrected me because it was first few and zero shot learners, and he told me that please change it. And I told him, come on, it's quite logic that you first try at least few shots, and then if you are very good, then you can do it in one shot or without a zero. And he told that it's interesting that first zero shot learners appeared, and then the few shot mechanism, the giving example of the model, that came. So that's the right order of the things. These two papers are extremely good, but I would propose to you to roll the shirt before you start it, because it's not easy for sure to get over that.